To power industrial motors and illuminate metropolitan grids, the system must generate and transmit alternating current at a scale defining modern infrastructure. Traditionally, wiring 3 separate single-phase transformers into one bank provided power, but required high volumes of iron and copper. Modern engineering favors integration. Combining all 3 phases into one unified system uses fewer raw materials, resulting in a lighter, smaller, and cheaper unit. This chart shows the ideal transformer model, a theoretical baseline engineers use before building a physical machine. It assumes a state of 100% efficiency, where the magnetic core and copper windings are completely loss-free. While that baseline is impossible to achieve in the real world, the history of grid engineering is a study in how to force heavy metals to perform as close to that ideal as the laws of physics will allow. Moving from theoretical models to physical hardware requires balancing 2 primary components: laminated magnetic iron and copper windings. This demonstrates the core-type architecture. Here, the windings are spiraled around 3 shared vertical legs of the laminated iron core. Notice the placement of the materials. Low-voltage lines are positioned closest to the core because they are easier to insulate. This strategic layering helps manage the thermal output and provides necessary electrical separation between the high and low voltage sections. The alternative is the shell-type construction seen here. Instead of sharing a central structure, it stacks 3 independent magnetic circuits on top of one another. While the stacked independent circuits of the shell type produce a less distorted electrical wave, the shared magnetic circuit of the core type is designed to exploit a specific interaction between the 3 electrical phases. This diagram shows the physical core legs arranged exactly 120 degrees apart. This layout mirrors the timing of the power supply: 3 separate alternating currents entering the windings, each arriving exactly 120 degrees out of phase with the others. Because of that exact timing, the magnetic fluxes induced by those 3 currents converge in the center and cancel each other out, resulting in a total magnetic flux of 0 at the intersection. Since the central intersection carries 0 magnetic flux, it performs no physical or electrical work. As shown in this engineering solution, that center leg of iron can be removed entirely, reducing the transformer's weight and manufacturing cost without sacrificing power capacity. By applying a physics equation directly to the machine's physical frame, engineers eliminate tons of heavy metal that would otherwise serve no purpose. Once the physical iron core is established, the copper lines must be routed using specific geometric patterns to interface with the grid. The Y topology ties all the windings together at a common central point. This neutral connection is essential for systems that need to output multiple different voltages from the same unit. On the right is the delta topology. Here, the windings are connected head to tail in a closed loop. This continuous chain provides high system reliability, which is why it is preferred for heavy industrial loads. There are constraints when mixing these shapes. For example, a delta primary feeding a Y secondary introduces a 30-degree phase shift between the input and output. This prevents the unit from being connected in parallel with symmetrical configurations. If the shared iron core is the hardware that determines the transformer's size and cost, these Y and delta configurations are the software, dictating how the machine communicates with the rest of the grid. This chart summarizes the advantages of the integrated design. It offers spatial efficiency, significant weight reduction, and lower initial capital costs compared to using 3 separate units. These machines are common sights in outdoor substations, where they provide the high-efficiency power distribution required for modern cities. However, the same integrated core that makes the unit so efficient also introduces a significant vulnerability. This is the shared core vulnerability. In a bank of 3 separate transformers, a failure in one phase only requires replacing one small unit. But because the 3-phase transformer shares a single core, a fault in any single phase shuts down the entire unified system. The 3-phase transformer is a physical manifestation of a wave equation. By integrating the 3 phases into a single core, engineers trade the redundancy of separate units for a smaller, more efficient machine, one where the failure of a single part shuts down the entire system.